All right, cool. So I know that the presentation should last roughly 1 hour, that we have some time for questions at the end, but feel free to stop me whenever you want in case there is something that is not clear and maybe you want me to explain again. Since there is a lot of content, I think it's better to stay aligned and probably not wait until the end. So, first of all, thanks for attending this presentation. So it's a pleasure for me to present this work, which was done in collaboration with Ryan Welch, a new PhD at Stanford University, and Aldo. So this was roughly a collaboration that started between Ryan and Aldo initially for his master thesis. Then when I started my postdoc with Aldo, I kind of joined in and tried to steer a bit the problem towards pure exploration. And first of all, probably it's a good idea to understand what do we mean by pure exploration. And I like this paragraph from this paper from Chernoff, Sequential Design of Experiments. And when you read this initial introduction, I think you can get a feeling of what do we mean by pure exploration. So imagine you're a scientist and you're trying to study something like a phenomenon. So you try some experiments, you try experiments one after the other, and you collect evidence. Finally, after some time, you have collected enough evidence that you are satisfied with your conclusion and you're ready to make your statement. So this is roughly what we mean by sequential design of experiments and by pure exploration. Pure exploration is simply the machine learning term for what a statistician would call active sequential hypothesis testing. And it's essentially just a problem of understanding what experiments you should do next so that you can collect evidence. And after a while, you have enough evidence to make a certain conclusion. So, in other words, we are trying to understand some underlying hypothesis. We are trying to understand some underlying theory. And there is the problem that we need to understand how to allocate experiments. What should you do next in order to maximize the evidence that you collect? And it's not only important to understand what experiment to do, but also when you should stop. So these are all questions that we will try to answer in this presentation. But before we move on, probably you already know the exploration exploitation trade-off in reinforcement learning. This is quite famous. And it's simply the problem that you want to try to maximize the reward. So you know that in reinforcement learning, there is this notion of reward function. We act in some environment, and by acting this environment, we observe rewards, and the objective is to maximize the total reward that you collect. But there is the problem that when you don't know which action is good, you need some kind of exploration first. So probably you will incur in bad rewards, you will incur in some penalties. And so there is this exploration exploitation trade-off that you need to take into account. But in pure exploration, we don't care about reward. So it's like the counter movement to regret minimization. So pure exploration just refers to how fast we learn, and we don't care at all about the reward. We don't care about how much reward we are going to collect. We only care about how quickly we can learn and how much evidence we can collect over a certain period of time.
Question:
Yeah,
if we don't care about reward, like how do we characterize learning kind of more quantitatively? Like how can we measure that we've learned something?
yes. So we need to think in terms of information. So the reward at the end shouldn't be human designed. As we will see later, actually a reward will appear, but this reward function is not something that you define. It should appear from the problem, actually. And this is nice because as we will see, this is a reward that is unbiased and it's an information theoretical reward. So it will match our intuition of maximizing evidence. But we will get to this later. So maybe we can also discuss this more in detail after, towards the middle of the presentation. So for what problem is this useful? For example, there is a recent paper where they use active sequential hypothesis testing to minimize the number of tests that you perform to detect cancer. You can improve recommender systems. You can use it for identifying faulty sensors. Or maybe you can use it to do active search on the celestial sphere. But let's maybe check some examples that we have in the paper. So in the paper, we have this nice example that is a digit detection problem. So you start with a blank image, so you don't know what is the image about, and I ask you to select some pixels. And one pixel at a time, you need to understand what is the image about. And you need to do it as quickly as possible. So now let's do it maybe by not pixel by pixels, but by patches of pixels. So we start with one patch, then you decide where to sample next, and you keep going until you understand what is the image about. So for example, ICP, the method that we propose, roughly takes on average 10 patches of pixels to understand what is the digit about. And this is a really nice example of pure exploration. Here, there is no notion of reward. There is just a problem of maximizing the information that you need to collect in order to classify the image. Another classical example is the best arm identification problem in bandits. So in bandits problem, you have a finite number of arms that we also call actions. And usually when you select an arm, you observe some random reward distributed according to some distribution with mean value mu a. And in best arm identification, the goal is to try to understand as quickly as possible what is the optimal arm, A star. A star is defined as the argmax of mu a. Here we have rewards, but we don't care about the reward that we collect. We only care about understanding which arm is the optimal one with some confidence level delta. But okay, so far it's all very nice. We don't care about rewards. We want to maximize evidence, but how do we compute optimal exploration strategies? How can we do that? And also, very importantly, why should the strategy be adaptive, right? I think it's quite intuitive. I think a truly intelligent agent should tailor exploration to the difficulty of the problem. Treating all the problems the same is not a sign of intelligent behavior. So obviously the solution should adapt to the problem that we face. It shouldn't be a solution that works like for all of the problems in the same way. Unfortunately, it's not easy to compute adaptive solutions. It's a hard problem, and so far we have solutions only for simple problems. And roughly, when you try to solve adaptive exploration problems, you end up trying to solve this minimax problem. So in this minimax problem, you have two players. You can think of players where there is one player that tries to do the exploration, and then there is nature, and nature is trying to make your life harder. So imagine you are like the exploration agent. Your goal is to maximize the evidence, and the notion of evidence can be quantified by this expected value of this KL divergence. So this KL divergence is taken between the dynamics of the problem that we are considering, T. X is the data that we sample from the environment according to the policy. So we have this rho pi that is the data distribution induced by the exploration policy. And then we have P prime. P prime is what we call a confusing model. It's chosen by nature, and it's chosen in a way such that it tries to minimize this evidence here. But P prime still needs to be different from P. It's different in a way that the underlying hypothesis that we are trying to estimate is different from the one in P. For example, let's say you are trying to classify an image, like the digit example from before. Maybe the true image is 9, the true digit is 9, but then the confusing model should be about some digit that is close to 9, but still different. Maybe it's 8. So solving an exploration problem usually amounts to solving this optimization problem. But the problem is it's not easy to solve. Only recently we know how to solve it for simple IID bandit models. And most results are limited to tabular problems, and extending to more complex setting is difficult. For example, for MDPs, the optimal expression strategy is characterized by a non-convex problem. And in some cases, it's not even possible to identify the true hypothesis. So what can we do to solve this? And can we come up maybe with a method that it's simple and doesn't require too much math? So this is what we try to do in this paper, in context learning for peer exploration. In this paper, we propose a transform-based architecture that we meta-train on a family of problems to learn an exploration policy. And ICP uses transformers so that we can do in-context learning. So at inference time, we can gather evidence on new tasks, and we don't need any parameter update of the network. So depending on the observation that it sees, it will automatically adapt to the problem. So I hope it's roughly clear so far. We are gonna now talk a bit about the modeling of ICP, some theoretical results, and then the practical design. So as I said before, we are trying to estimate some underlying hypothesis. The model, the problem can be modeled in this way. We have some exploration agent that is interacting with an environment. You sequentially select actions or experiments or queries. These are all different terms that we can use to denote AT. And after we select an action, we observe some outcome from the environment, xt plus 1. So we model this problem first by defining what is the hypothesis space. It can be finite, it can be continuous, but in this paper we consider only finite hypothesis spaces. We can define what is the action space, the observation space, and also the dynamics of the environment. And here the dynamics can be history dependent, can also be non-stationary, and it models what is the distribution of the next outcome based on all the past history. But what about the true hypothesis? So for the true hypothesis, we make the assumption that there exists some functional H star that maps dynamics to hypothesis. And we model H star, the true underlying hypothesis, to be little H star of P. So at the end, we can define an environment to be this tuple, XAP H star. And to make things a bit more clear, we can maybe look at the bandit example from before. So in the best arm identification problem, we can simply define H star to be argmax A of mu A. So here the functional is the argmax. P is the reward distribution condition on the action that you selected. So after you select an action A, you observe X sampled from P given A, the reward. So the last ingredient that we need is also to have to define what is the prior over problems or prior over a set of environments, which represents our belief of what is the true environment. So after we have basically all the ingredients, but what should be the objective? Before I said, yes, we need to maximize the evidence, but exactly what do we mean? Well, recall the paper from Chernoff. Here we have some intuitions. We need to gather evidence so that you can make a certain conclusion. Um, this conclusion can be made over after a fixed horizon, or it can be made after you have collected evidence so that you are confident about the conclusion that the statement that you want to do. So the objectives that we have at the end are two: fixed budget, where you try to maximize evidence over a horizon, or fixed confidence, where you try to quickly collect evidence subject to some confidence criterion. And more precisely, we can define the problems in this way. So in the fixed budget problem, you're given an horizon, and the learner chooses a policy and an inference rule maximizing this objective. So the policy is the exploration policy. And the policy, this policy basically decides how to explore, which action to take. And the inference rule, it's simply a rule that defines what should be the estimated true hypothesis. So here in this objective, you can see that we are trying to maximize P and pi and I so that we maximize this probability here. So this is the probability that we estimate the true hypothesis. The inference rule depends on the data we have collected so far. And this data depends on how we choose pi, the exploration policy of the agent. And pi, you can think of it as a mapping from data to distribution of our actions. And as I said before, I is simply a mapping from data to hypothesis. So this is like a maximum likelihood estimator in the end. But one thing to remember is we, in some problems, the maximum likelihood estimators sometimes not the optimal estimator. And also we don't want to encode what should be the estimator. We want the model to learn not only the exploration policy, but we also wanted to learn what is the optimal way to estimate the true hypothesis just from the data. In the fixed confidence problem, we have a similar setting. We still have this probability of estimating the true hypothesis, but now we have this variable tau, which denotes the number of samples. So tau is also something that we need to optimize. And now we are trying to minimize the average number of samples that it takes to reach a certain confidence level that we have estimated correctly the true hypothesis. So like before, D also represents the data, but now it's up to time tau. Tau, it's a random variable. Pi is the same as before, and also the inference rule is the same as before. Okay, well, all very good so far, but it's a bit tricky. How do we learn pi, I, and tau? How do we even optimize this objective using a simple approach? How do we even solve the fixed budget objective? Well, as we discussed before, probably there is a way to actually define a reward function for this problem. And intuitively, yes, it makes sense that optimizing a policy, you can use maybe RL. And as we see later, learning I is also a very simple problem when we use supervised learning. But before we do that, we need a bit of theory to show that we can actually use RL and to try to understand what is the right way to do it. So I will try to keep the theory as light as possible. But the first thing we should notice in the problem is that when we try to optimize the inference rule I, since we have a prior, it makes very sense that the estimator we end up with in the end will amount to computing some posterior distribution. Secondly, the policy pi, as we will see, can also be learned using RL with an appropriate reward function. And as we will see now, the reward function emerges naturally from the problem formulation. It's not something that we define, but it's something that appears from the problem, which is very important here. Okay, but let's start from the inference rule. So the first result that we have is that the inference rule, the optimal inference rule maximizing the probability that we estimate the true hypothesis, is simply given the argmax of the posterior distribution. So the optimal inference is the hypothesis that maximizes the posterior distribution of the true hypothesis. And very importantly, this does not depend on the policy. It does not depend on the policy, and this is not something obvious to say initially, especially when you work maybe with infinite dimensional environments where the trajectory could be possibly infinite dimensional. But these results holds in general, which is very nice. And the idea is to simply use this result to show that we can use RL. For example, in the fixed budget setting, we can show that after applying this optimal inference rule, you can rewrite the problem from this that you see on the left-hand side of the equation to simply maximization over an expected value. And I use the notation R because in the end, this is exactly the reward that we are gonna maximize, and the reward is simply the maximum of the posterior distribution of the true hypothesis. So in the end, yes, we can use RL. This is the reward that we are gonna use for the fixed budget. And this is something that simply appears from the problem formulation. Simply by maximizing the inference rule, finding what is the optimal inference rule, and then plugging this optimal inference, you can show that in the end, you end up with this optimization over pi that is simply a maximization of a reward function. But now this is a bit funny because we are using RL to solve an expression problem. So it's like hiring a tour guide who asks you to show them around first. And I think it's also a bit philosophical here. Can we say that in the end, it's always about using RL in sequential decision making? It's not clear. It's not clear also to me. You could probably define the problem like in a way that it becomes recursive. For example, you could define the underlying true hypothesis to be about finding an expression policy, estimating some optimal expression policy. But then you need to solve the problem of finding an expression policy to estimate an expression policy, and you can define this kind of recursive thinking that it's not clear even if it ends, if there is a fixed point. And this is like an open question. But aside from this philosophical perspective, we can now show what is the optimal policy. And by using the reward that I showed you before, we can show what is the optimal policy. And the optimal policy is simply the greedy policy with respect to a certain Q function. And this Q function is defined in this way here. So the Q function at time t, given the data we have observed so far, it's an integral over the next value when we integrate over the posterior distribution of the next observation. And the final value, it's simply given by the reward function at the last time step. So at each time step, the optimal policy is simply defined by the Rmax of the Q function. So the only problem is trying to compute this Q value. And then once you have the Q function, you can use it to compute the optimal policy. So we can also do something similar in the fixed confidence. But here we also have the number of samples tau. Formally, it's called a stopping rule. And this stopping rule, you can think of it as some kind of function that, given the data we have observed so far, tells you if you should stop or if you should continue. So from this idea, probably you can understand that we can simplify the problem. We can simplify the problem by simply defining a stopping action. And we augment the action space by including the stopping action. And basically, the simplification is about letting the policy pi decide when to stop. So we don't need to find what is tau, but we simply let the policy learn on its own what should be the right times to stop. And formally, we define the stopping tau now to be simply the first time step at which the policy selects the stopping action, a stop. The second simplification that we do is to actually study the dual problem, which is a tad simpler. And from the dual formulation, we can also see how we can use RL. So we first then define the dual problem. You can see it here. We have lambda, our Lagrangian variable, and then we have this supremum over pi and I of v lambda pi I. And v lambda pi I is simply this dual formulation. So can we use the optimal inference rule from before? Yes. We can now also simplify the problem using a reward function, but it's not immediately clear that we get the guarantees that we want. We need to make some assumption actually to show that an optimal policy solving this problem, given an optimal value of lambda, it gives you a delta probably correct method. But this is a detail that it's more discussed, is discussed more in detail in the paper. But first, let's see the RL formulation. So the function here, v lambda, as you can see, it's basically made of two terms. There is a first term that accounts for the number of samples that you need on average. And then there is this second term that accounts for the evidence. And this term here multiplies lambda, the Lagrangian variable. So what we do is to define this reward function. So we define a reward function that penalizes every time step where you don't select the stopping action. And then it gives you a positive reward whenever you stop. And this positive reward is going to be proportional basically to the probability of the posterior distribution evaluated at the maximum. And this is multiplied by lambda. So using this reward, we can now define the Q function. So the Q function at some point in time, given the data you have observed so far, will be simply this reward function plus the expected value of the next Q function, the next time step. And here, notice that we average over the posterior distribution of the next observation. And this expected value is also multiplied by this indicator function that we are not selecting the stopping action. So whenever we select the stopping action, the Q function will be simply equal to this quantity here, lambda, that multiplies the maximum of the posterior distribution. And if not, it will be simply equal to -1 plus the expected value at the next time step of the Q function. So given these two equations, we can also show that the optimal policy for any value of lambda is simply the argmax of some of this Q function. And under some identifiability conditions, it's also possible to show that any maximizer lambda star guarantees that this policy here, pi star of lambda star, satisfies the delta correctness criterion. So all of this is very nice. We can do RL. And these results now motivate how we are gonna use ICP in practice. So we can do RL. We have defined this reward function, but what are we gonna do in practice? We also have prior. So maybe we can sample from these prior trajectories and use these trajectories maybe to learn pi and I. So the idea is we have this prior, we assume we have some kind of simulator that can sample from this prior, that can simulate trajectories that we can interact with. So we can use this data to learn pi and I. And then once you have pi and I, you can apply this policy at this inference rule on the real problem. And yes, we use transformers so that we can handle sequences of data that can be of variable length. So ICP will split into phases. There is a first phase that is the training phase. So in this phase, we are collecting data from the simulator, and we use this data to improve the exploration agent and the inference rule. So we see here there is this exploration agent that selects actions. Then the environment outputs the next observations. This observation is used by the inference rule to compute the posterior distribution, and this is used to compute the reward function. So at training time, ICP interacts with the simulator. In each episode, in each epoch, we draw an instance from the prior, we generate the trajectory, and this trajectory will be saved in some buffer that we use to store the training data. And then after we have learned the inference rule and the exploration policy, at inference time, we simply apply the exploration policy to collect data from the environment. And whenever we stop, we will use this data to make a prediction of what is the true hypothesis. So let's go and define the loss function now. We have these three equations, right? So we have the equation for the inference rule, for the optimal inference rule. We have the reward function for the exploration policy and the Q function. And here, just for simplicity, we only look at the fixed confidence. For the fixed budget, it's very similar. So first thing first, we can learn the posterior distribution of I. So we don't learn directly the argmax. We can simply learn the posterior distribution. And we can do this by a cross-entropy loss, for example. And using this posterior distribution that we learn, we can also define the reward function in this way. So notice that now this term here, we switched it with this one. So this max over h of I h given dt. So we are gonna use a cross-entropy loss to learn I, and your favorite DQN technique to learn pi, basically. So we parameterize the inference rule by some parameter, and we train it with this cross-entropy loss. We sample a batch of data from the buffer, and we simply use this loss, which in the end is equivalent to minimizing the KL divergence between I and the posterior distribution up to a constant. While for the exploration policy, we need to use some tricks to stabilize the training. The first trick is to use a target network for the inference rule. So if you're not familiar with target networks, these are used, for example, in DQN. They are used to stabilize training, and the idea why we need a target network is because we don't want the reward function to change too quickly. We want it to be as stable as possible, so that we can learn the Q values in a more stable way. So given that the inference network is changing, because we are training it to learn the posterior distribution, we try to slow down it by using a target network. So we use a target network here in the definition of the reward. And we can also define then what is the Q function here. And as you can see, also in the Q function, we use a target network. But this is basically DQN. There is also another trick that we use that I will not go into the details here, but we don't use this lambda exactly in the way that you see here in the equation. Because lambda multiplies I, and at the end, we are gonna also update lambda. So this product between lambda and I is not very nice. So in the end, what we do is to instead define a cost variable. So the reward that we at the end optimize is gonna be minus cost minus C plus this max over H of I. But this is something that we discuss more in details in the paper, in the appendix. Okay, but let's pretend that we use this formulation for now. So we have this reward, we have this key function. We can use a DQN-like loss. And we can actually define it in this way here that you see in equation 4 and 5. So this loss will be, it's made of two terms. So the first term refers to the TD loss, the temporal difference loss, whenever we select an action that is not the stopping action. So when we don't select the stopping action, we can see that it's going to be -1 plus the next value minus the current value. So this is exactly what we try to minimize. But whenever we stop, the Q function will simply be equal to lambda max over h of this inference rule evaluated at h. And this is something that we can always evaluate. It doesn't depend on future data. So this Q value of the stopping action can be updated at any time. So basically, it allows some kind of retrospective evaluation of stopping. So this is something that will speed up training a bit. It's not essential, but it will speed up training a bit. So this is basically it. There is not much more, except that we also need to update lambda. We are simply going to use a gradient descent update and just a very simple update where here you can see lambda is updated with some small learning rate beta. And here we have this hat p that denotes the empirical accuracy that we have. So at p is computed using k-IID trajectories, and we use these k-IID trajectories to evaluate what is the current estimated accuracy. So at the end, ICP is simply consists of using those lossless function and updating this Lagrangian variable. And there is not much more. It's a very simple method. We sample an environment from the prior, then we use this Q function that we are learning to select the actions, and note that we are being greedy with respect to this Q function. We store the partial trajectory that we observe in the buffer, and then after we have collected one trajectory, we sample a batch from the buffer, and we use this batch to update the networks using the losses that I showed you before. And we also update the Lagrangian variable according to the equation I showed you before. So after we have learned pi and I, then there is the inference phase where we simply use pi to collect data. And then at the stopping time, we can return what is the predicted hypothesis given the data we have collected so far. Okay, so finally, we are the numerical results, but I'm gonna just give you some simple examples. There are more examples in the paper. We have some generalized search problems. We have best arm identification problems. But now we look at three simple problems. Can ICP, for example, learn binary search? This is an example of generalized search. The example I showed you in the beginning, pixel sampling for classification. And then one of our favorite, can ICP discover and exploit hidden information in best arm identification? So starting from the first, this is a really nice example of meta-learning an algorithm. So here we are trying to meta-learn binary search. We have a vector with k elements, and we are trying to find some element in this vector, h star. I assume all of you are familiar with binary search. Here, whenever we select an action, we are selecting an index, and we observe -1 or 1, depending if the index that we selected is smaller than h star or not. And ICP, it seems to be able to learn how to do a form of probabilistic binary search. Here you can see the vector size and also what is the average stopping time for ICP, so the average number of samples needed. And surprisingly, even if we set accuracy 0.9, it seems to always be able to hit accuracy 1. and it uses an average number of samples that is smaller than the maximum stopping time for the maximum number of samples needed for solving binary search. Then there is the classification problem, so where we select patches of pixels and try to understand what is the image about. But there is something tricky here, because in this example, the digits are always in the center of the image. So it's not really clear if ICP is learning an adaptive strategy or maybe just sampling at random in the center. So what we did was to compare ICP with uniform policy and with a deep contextual version, so a deep contextual multi-arm bandit algorithm. So we tried to compare how these different methods select the patches in the images, and we used a pairwise chi-square test to understand the similarity. So here in this diagram, you can see whenever you see a chord between two digits, it means that there is some kind of correlation. So sampling in those two digits is very similar. So the thicker the chord and the more the more similar it's the sampling. So as we can see, for ICP, there is some similarity between 3 and 8, which makes sense, I suppose. But overall, there is a stark difference between ICP and uniform and this deep contextual multi-arm bandit. These two methods don't really seem to be adaptive, don't really seem to adapt to what is the underlying true digit, while ICP in reality seems to adapt very well. And also when we look at the average accuracy and the average number of patches used by the methods, we also see some difference, and also the accuracy is much larger for ICP. Lastly, we have this bandit problem that we call the magic arm problem. So this is a bandit problem where there is some arm with hidden information. So there is one of the arm that encodes information about the index of the best arm, and we call this arm the magic arm. So let's say we indicate by M the index of the magic arm. We denote the average reward for this arm by phi of A star. So this phi is simply some invertible mapping, phi. And A star, remember that is the index of the best arm. So if you know this mapping and you can invert it, then you can immediately identify what is the best arm. So that's why we call it magic arm, because basically if you know this mapping, then you can immediately understand what is A star. But the twist is that we don't tell the model what is this mapping. We want the model to learn what is this mapping on its own. And then we define the rewards to be Gaussianly distributed for all the actions. And we also define the variance to be function of the standard deviation of the magic arm. So we define sigma m to be the standard deviation of the magic arm, and the smaller is sigma m, and the more likely that we should sample this magic arm intuitively. And indeed, this is what seems to be happening here. So we compared ICP with information-directed sampling, which is a BI method based on posterior sampling. And here we have different plots. On the left plot, you can see what is the average number of samples needed to identify the best arm. And we, on the x-axis, you can see what is the standard deviation of the magic action. So when the standard deviation of the magic action is 0, then sampling the magic action tells you immediately what should be the optimal arm if you can invert the mapping. And as we can see here, the both methods are able to basically invert this mapping, learn what is it about, and in one sample, identify immediately what is the best arm. But what's more interesting is, can ICP balance the sampling of the arms as the standard deviation increases? will it learn also to sample the other actions and understand how to mix this information together to identify what is the best action more quickly? And indeed, this is what we observe, that it manages to beat IDS. And on the right plot here, you can see also the fraction of times the magic action was sampled as you increase the standard deviation. And also the accuracy, so the correctness remains pretty stable around 0.9, which is our target accuracy. So I hope this was clear, and I thank you for reaching this point. I think there are still plenty of questions open, and we also look forward to collaborations if you want. One simple question is, are transformers really a good neural architecture for sequential problems? And how can we enable long context? We also made an assumption that we have a simulator, but what if the simulator is not really perfect? What if there is some misspecification? Another interesting question is, can we move from a Bayesian setting to a frequentist one? So basically, we remove the prior and instead model the problem as an adversarial problem where there is an adversary choosing the model. And lastly, there are also a lot of theoretical questions left unanswered. I think we just scratched the surface of this problem. But for this, maybe you can contact me for details. But thank you for listening. Yeah.
Any questions? Anyone, any questions from online? Okay, I guess another round of applause for this year.
Thank you. I hope it was clear, the reward function, how it comes into play, and I hope it answered your question about the reward.
And I think that made clarify that point very well earlier on. Thank